Hello everyone, welcome to ILTA Physics Online. Today, we're going to be studying the center of gravity of an object. The center of gravity is the perfect balance point of an object. What would happen to a pencil standing at an angle on one of its edges, like in the diagram on the right? It's going to fall over. So, what exactly causes the pencil to tip, and why does it happen? The physical concept we use to explain this is the center of gravity, which is what we're going to study today. In physics terms, it's a hypothetical location where we imagine all of the object's weight is concentrated at a single point. It can be a bit hard to imagine all of an object's weight being concentrated at a single point. However, it might help to think of it as being similar to the particle model we use to analyze motion, where we represent a moving object as a single dot. Wait, we've been studying rotational motion, right? So you might be wondering, why are we suddenly talking about the weight of an object? Does that even fit here? Actually, it does. The word weight refers to the force of Earth's gravity pulling an object toward its center. And since force acts in relation to a rotation axis, it creates torque, which makes the object rotate. So what we're going to do today is first understand the torque that gravity exerts on an object. Then we'll study the concept of the center of gravity, which is essential for analyzing that gravitational torque and rotational motion. This relationship between the center of gravity and torque is very closely tied to an object's stability. Finally, we'll derive how to calculate the center of gravity for objects with simple structures and look at the relevant formulas. The symbol for the center of gravity looks like this. All right, let's briefly review the rotational motion concepts we've learned so far and then dive into the center of gravity. From a kinetic perspective, force is the source that accelerates an object in linear motion. This means if you push an object with force, it accelerates and moves with a certain velocity. In the same way, torque is what causes an object to rotate. It's the rotational equivalent of force in linear motion. As you can see in the diagram below, to analyze rotational motion, we first need a pivot, the axis of rotation, and the location where the force is applied. Once those are set, we can define a radial line connecting those 2 points. The torque that makes an object rotate is proportional to 2 physical factors. First, the distance between the pivot and the point where the force is applied. Second, the component of that force that is perpendicular to the radial line. Based on our everyday experience, any force acting parallel to the radial line doesn't contribute to the rotation at all. We can express torque with this formula. Please take a close look at the units for torque again. If multiple forces act on different positions of an object, the net torque causing the rotation is the vector sum of all those individual torques. One thing to be careful about when calculating the vector sum of all individual torques is the direction or the sign of each torque. We've defined the counterclockwise direction as the positive direction for rotation. The second thing to remember is that any force acting directly on the pivot point does not contribute to the torque at all. This is actually a very important physical concept that we'll apply today to calculate the center of gravity. Now, with this physical understanding of torque, let's study the rotational motion created by the gravity. All right, everyone, let's consider a pencil, as shown in the diagram below, standing at an angle with only one edge touching the desk. This pencil will undergo a rotational motion, falling downward with that edge serving as the pivot point. Come to think of it, a tilting pencil falling over should indeed be analyzed as a type of rotational motion. So let me ask you this. What is the cause of this rotational motion? In other words, what is the force responsible for this? A force acting on an object creates torque that leads to rotation. In this case, it's gravity, the force pulling the pencil downward toward the earth that causes it to fall over. This is because gravity acts on every object on Earth with the same magnitude relative to its mass. We call this weight. In equation form, W equals m times g. Now, let's try to calculate the torque caused by gravity on this pencil. As we saw earlier, the torque caused by a force acting on a specific spot can be calculated with a standard formula. When a force acts on one specific point of an object, we calculate torque by multiplying the distance from the pivot by the force component perpendicular to the radial line. So, in the case of this tilting pencil falling down, where exactly is the force of gravity called weight acting? Is gravity acting on the black tip at the very end? Or is it acting somewhere in the middle? Maybe it's acting right at the pivot where it touches the desk? The correct answer is, gravity acts on the entire object, every single part of the pencil. And then, how do we calculate torque when gravity is acting on the entire object, meaning it's pulling on many different spots at once? That is exactly why we need the concept of the center of gravity. Let's think again about the rotational motion created by gravity. The image below is a snapshot of a gymnast performing on a high bar. As shown in the left image, the gymnast is rotating back and forth using the high bar as the pivot. At this time, gravity is pulling down on every single part of the gymnast's body. These are the forces represented by the red arrows in the left image. To analyze this rotational motion, let's imagine that all the gravity acting on the gymnast is concentrated at one single point. We can then analyze the motion by assuming that the total weight of the gymnast is applied only to that specific spot. We define this single point, where we assume the entire weight of the object is concentrated for the sake of analyzing rotation, as the center of gravity. The symbol for the center of gravity is usually shown like this. I'm borrowing these images from another textbook because they're the best ones I could find to explain this. You can find the source in the notes below. The concept of the center of gravity plays a crucial role in analyzing rotational motion. To put it another way, it's the difference between a pencil standing straight up, which doesn't fall over, and a tilting pencil which rotates and falls. The physical phenomenon related to the center of gravity in rotational motion is what we call stability or balance. We'll just quickly go over the basics of stability for now. In the bottom left image, a father is balancing a child on his hand. As shown, if the child's center of gravity and the pivot point, the father's hand, are perfectly aligned vertically, gravity doesn't create any torque. Therefore, the child doesn't fall over, meaning no rotational motion occurs. However, as seen in the right image, if the center of gravity and the pivot are not aligned, the torque acting on the center of gravity causes the object to rotate and fall. This relationship between the center of gravity and the pivot point for maintaining balance applies whether the center of gravity is above or below the pivot. One thing to add is that, to be physically precise, the center of gravity and the center of mass are actually different concepts. However, when we're in a uniform gravitational field like Earth's, you can practically treat them as the same thing. So, how do we actually calculate an object's center of gravity? In everyday life, you can find it experimentally by seeing where an object balances horizontally. But here, we're going to derive a quantitative way to calculate it. First, the bad news. We can't really calculate the center of gravity for objects with completely random, arbitrary shapes using simple quantitative methods. But in a way, maybe that's good news. However, we can calculate it for very simple and typical shapes. For example, a dumbbell-type object. The physical concept we use to find the center of gravity is that the net torque is zero at the pivot point. In other words, the location where the object is perfectly balanced and doesn't tilt, the state of no rotational motion, is the center of gravity. Make sure you have a clear understanding of this concept. If you need to, feel free to pause the video and think it over for a moment. Let's use this fact to calculate the center of gravity. Consider an object, like the one in the diagram below, where two different masses are connected by a thin rod. Let's call it an unbalanced dumbbell. To calculate the center of gravity, we first set up an arbitrary coordinate system to define the positions of each mass and the center of gravity. In this case, we can expect the center of gravity to be located somewhere between the two masses. Now let's calculate the torque at each mass's position. First, let's look at the torque for the first mass on the left. According to the formula, torque is the distance from the pivot multiplied by the gravitational force, the weight. So, the torque for the first mass on the left looks like this when expressed using coordinates. In this case, the radial line and the direction of gravity are perpendicular, so we don't need any sign terms. Also, let's think about the direction of rotation. The direction is indicated by the sign of the torque. For mass 1 on the left, gravity pulls down and the pivot is to the right. This means the torque would cause a counterclockwise rotation, so we mark it as positive. When you're doing the actual math, you don't need to write out the plus sign if the number is positive. Now, let's calculate the torque for the second mass on the right. Using the same formula, it's the product of distance and weight. But the important part here is the sign. For the second mass, since the pivot is to its left, the force pulls it into a clockwise rotation. Therefore, the sign of the torque for the right mass is negative. Direction and signs are very important when calculating torque, so please make sure you understand this clearly. Now, let's find the net torque acting on the entire dumbbell. The net torque is the vector sum of all torques. Remember, if the pivot is located at the object's center of gravity, the net torque will be 0. Here is how we express that in an equation. If we rearrange this equation for the center of gravity, we can calculate its coordinates like this. In the final formula, you can see that the numerator is the sum of the products of mass and position, and the denominator is the total mass. In this page, I've summarized the 4 steps to calculate the center of gravity for more complex objects. Let's calculate the center of gravity for an object where masses are connected by thin rods on a 2D plane as shown below. First, set up an arbitrary coordinate system for the given problem. Second, represent the position of each mass's x and y coordinates using that system. Now, calculate the x-coordinate of the center of gravity using the method we derived earlier. As explained, the numerator is the sum of mass times position, and the denominator is the sum of all masses. Then, you can calculate the y-coordinate of the center of gravity in the exact same way. Like I said before, we can't easily find the center of gravity for totally random shapes through simple calculation. But for objects with specific shapes or arrangements, we can use this method. But I know what you're thinking. This kind of shape we just worked on isn't exactly common in the real world. So why did we bother deriving the center of gravity for something like this? In the next section, let's look at how we can apply these concepts to some real-world problems. Finding the center of gravity for general objects usually requires calculus, so we won't cover that directly here. However, the idea we just discussed can be extended to analyze more complex shapes. On the bottom left, there's a picture of 2 children balanced on a seesaw. This isn't just one object, but a system. We're looking for the balance point, or the center of gravity of that system. You can use the same unbalanced dumbbell idea. Just apply the physical fact that the net torque is 0 when the pivot is at the center of gravity. The image on the bottom right shows a cheerleader's movements. For complex shapes like this, we divide the entire object into several smaller parts and calculate the center of gravity for each part individually. In this image, the cheerleader's body is divided into 2 arms, 2 legs, and torso, and the center of gravity for each part is found. By doing this, you can treat the whole object as a system of several masses connected at specific locations, like what we just learned. Then you find the center of gravity of those individual centers of gravity to get the total center of gravity. Of course, I didn't explain the exact process of finding the center of gravity for each arm or leg, but this illustrates the idea of breaking down a complex object into smaller parts for analysis. That's it for today's lecture. Great job, everyone. See you next time.